Thank you very much, Misha. Okay. I suggest we move on to the next speaker, which is Milind Buddhikot. He's a member of the technical staff in the Networking and Network Management Research Center at Alcatel-Lucent Bell Labs in Murray Hills. He's a Doctor of Science and Computer Science from Washington University, and his main research topics are in the area of systems, protocols, algorithms, security, and end-to-end applications for dynamic spectrum access and cognitive wireless networks, green wireless, and network virtualization and sharing. He's as well author of over 30 research papers and holds 8 patents and more than 20 pending patents.
Is this on? Good, I think it's on. So first of all, thank you to Telephonic for this opportunity to come and present in this very interesting workshop. My name is Milind Buddhikot. I'm based in Murray Hill, New Jersey. And even though only my name is here on the slides, this is joint work with a lot of my summer interns, and the work is influenced by collaboration with a lot of my Bell Labs colleagues as well as my external collaborators in the university. So let me get started with my presentation here. So I think the way I'm going to go about it, I'm going to quickly review the motivational stuff for my work, and then give you 2 specific case studies that are going to substantiate my talk message. So it's already sort of covered in the talk that the data traffic is exponentially increasing in coming years. By some estimates, by 2018, it would be up by about 100 times. And if you require increased traffic support, you have to increase the capacity within the network also proportionately. And that requires new infrastructure, and the infrastructure deployment often tends to be very capital and operating expenditure intensive, right? So if you're an operator like Telefonica, unfortunately, life is not very easy. You're facing certain dilemmas. First of all, as Caetano already pointed out in his talk, and it's as if 2 of us have talked to make these slides together, but it's not. The first dilemma is that adding new users doesn't necessarily linearly increase your throughput. Actually, it has been shown that the ARPU actually starts decreasing. So the only way if you want to run a profitable network is to actually control the network costs. The second dilemma is that not all cell sites or all parts of the network are created equal. Roughly 50% of the revenue comes only from 10% of the cell sites. Roughly 80% of the revenue comes from 30% of the cell site. So there's a large fraction of the network that is actually not contributing tangible revenue to your network. And that's a very dangerous scenario, because if you can create an alternate network deployment and network architecture where new operators can emerge and target only 10% of your cell site, your 50% of the revenue is potentially pressured, right? And that's a very dangerous scenario competitively. It can disrupt the operator ecosystem significantly. The third thing that is emerging is that the applications that are being deployed are necessarily very unequal, and they're very different than the voice traffic that we are historically used to. So the traffic requirement goes from hundreds of kilobits per second or few megabits per second to few kilobits per second in different locations, different times, different uses, right? And that means that the static allocation of resources is not going to work. And it's a strong statement, but I do believe it's not going to work in the long term. And you need dynamicity in your every bit of network decision-making and operation, right? So if you are an operator, traditionally you have had multiple license bands, and you are operating a macro cellular network. And if you want to increase capacity, there are only so many ways that you can do it. First, you try to increase your bits per seconds per hertz, your spectral efficiency. So you go and start operating networks with wider bands, as in LTE is a good example. Or you go and try to increase your spectral efficiency by doing MIMO. And good examples are the newer technologies like COMP and hundreds of antennas that are emerging on the scene, right? The second way is to go and increase your bits per seconds per hertz meter square spectral efficiency. So you start deploying small cells and outdoor metro cells. Unfortunately, if you are an operator and you have only fixed band licenses, all these dense networks are going to essentially use the same common channel bands. So that's going to lead to increased interference interactions. It's going to come to a point where my contention is that your performance gains are going to reach a limit, and the proportionate complexity and cost and gain trade-offs are going to start weighing on the network costs. So the immediate and obvious solution is to go and increase the spectrum that is available to you. And let's see if you can easily add more spectrum. So if you look at the US case, roughly over the period of last 15 years, the amount of cellular spectrum has approximately tripled from about 170 megahertz to 534 megahertz. And projections are that you are going to need much more spectrum. Anywhere from 1.2 to 1.7 gigahertz of new spectrum is expected to be required to operate your networks at the expected demand levels in terms of capacity, right? So if you talk to different companies, they'll tell you what kind of spectrum they are looking at. As an example, Verizon is saying up to 100 megahertz over the next 5 years, right? So the question is, okay, sure, we want more spectrum. Is it easy to get spectrum? Unfortunately, that's not true anymore. If you look at the US case, the so-called AWS spectrum that is now being considered for deployment, it took about 6 years to actually go through the process of making it available, auctioning it, and start offering some service. And it's not even at full rate, so to say, right? And if you want to continue in the old model of licensing, you don't really have much hope, because first, it takes too much time. Second, there isn't enough spectrum available to do old form of auctioning, because in 2009, only 50 megahertz of new spectrum was made available. And if you guys are following what's happening in the Washington, DC, in terms of incentive auction to make more spectrum available, it's already clear that incentive auctions will never probably happen. So forget about making any new spectrum available through incentive auctions, right? So the bottom line is you need new kind of spectrum access model, new ways of accessing more spectrum. And as soon as you introduce those, that has a potential for disrupting, again, the whole ecosystem. It can impact the existing operators. It can create new market structures and new competition, right? So an important factor to look at is the energy footprint in the network. If you look at it, I don't know if the pointer works or not, but anyway. So roughly 10% of the energy footprint of the entire operation goes into only the user devices. Roughly 90% goes into the network. Out of the 90% of that cost, roughly 80% is going into the base station itself. And if you look at the macro cellular analysis, roughly 50 to 80% can go into the power amplifier and the feeder structures, right? So especially in developing markets, it's clearly that even in the existing scenario, the energy cost is a significant cost, because often fossilized fuels like the diesel is used to run the macro cellular side. As you go more and more towards dense small cellular networks, this doesn't necessarily apply as much, because the power amplifier is not a dominant cost, but the signal processing becomes a dominant cost. So all of a sudden, with hundreds of thousands of small cells in the network, you still have to start worrying about the energy costs. So in terms of how do you go and tackle these challenges, my work is primarily, you can think of it as looking for new paradigms for addressing these challenges. And the way we are articulating is that the main thrust of addressing this challenge is what we call as dynamic sharing of spectrum. And essentially, when a resource is limited in amount, the only way to make it available to more people and to get maximum benefit out is to share it. And the sharing is actually enabled by 4 different ideas as such. The notion of sort of variable grade unused or unlicensed spectrum, variable grade of even licensed spectrum, the notion of spectrum agile wideband radio. And I fundamentally believe that even though SON is becoming a very important thrust area, infrastructure is still going to play an important role. So exploiting lightweight infrastructure to impose better coordination, better control to maximize efficiency of the network, right? And all of this can potentially lead to high capacity, energy efficient cellular networks. And let me run through 2 specific use cases or specific examples that we have worked on. So by variable grade licensed spectrum, we mean if you look at an operator, often the spectrum resources span over different bands, ranging from 700 to 2.6 gigahertz spectrum. And all of these spectrum bands have very different characteristics in terms of the amount of spatial coverage that you have, the kind of power you can transmit, the kind of channel mass you have to support, and also they have very distinct propagation characteristics. So instead of operating networks independently in each band, can you exploit these bands in an integrated fashion to optimize the network performance and the energy consumption? The second case is the so-called the white space spectrum, where this is a famous 2002 measurement that was reported in an NSS study that was funded by National Science Foundation, which showed that even though majority of the spectrum below 3 gigahertz is allocated, a large part of it is highly underutilized or unused. And this spectrum became famously called as a white space spectrum. And if you want to free the spectrum using the traditional licensing model for use, it's highly unlikely to happen, as we already pointed out. So the natural question is, can we exploit this white space spectrum in a smart way, especially if the radio technology makes it possible to do so? But unfortunately, the white space comes with its own burden. So because it has very different characteristics. First of all, it's very disparate in the spectrum locations. It can go from all the way from 200 megahertz to 3 gigahertz. So your radio better be able to dynamically tune to this band if you want to exploit them. Typically, these are already allocated to somebody. So there's a primary user who owns the white space band. So you have to be cognizant of the characteristics of the primary band. So as an example, if you have a TV band, digital TV white space, the band is either in use by a TV transmitter or it's sporadically used by a wireless microphone. If you're looking at radar bands, they're either predictably used or predictably empty, right? If you're looking at public safety channels, they have very varying degrees of load factor. At some points of the day, they have high utilization, and certain emergency emergency situations, they have very high utilization. But large part of the day, they could be underutilized, right? So also the temporal and spatial scale of availability of the spectrum is very different. So if you want to use this variable grade spectrum in your network, the challenge is going to be, how do you create a robust system that has guarantees very similar to licensed band spectrum that is available all the time and with guarantees? So is there technology available that can take these variable grade spectrum and tie it into a cellular network to retain the same experience that we have come to expect, right? The other driving factor is the so-called wideband radios. As I already mentioned, if you want to exploit white spaces, you better have a wideband radio, and those are already becoming possible. So they allow you to go from 5, 10, 20 megahertz, and 40 megahertz is already on the horizon. And they allow you to also support digital processing of RF baseband in software, either in a centralized place or in a localized node. And that allows you to so-called do dynamic measurement, monitor, and modify the network performance, the so-called cognitive cycle that has been talked about. But in our case, cognitive cycle is not with localized decision-making necessarily. And it allows you to then change the node and the network characteristics on the fly. And a light radio is a famous, recently announced example of a wideband digital tunable radio that we believe will help us drive the kind of ideas that we are talking about here. So let me describe a specific case study. This is a project that has been going on for the last 3 years. The main objective over here is to build what we call as ultra-broadband dual or multi-technology small cells. So the idea here is that if you have multiple of these homes, each of these homes has what we call a white cell deployed, which is an indoor small cell or outdoor metro cell. And each of this femtor small cell has a built-in wideband spectrum sensor in it. And the end user devices are also wideband and capable of operating in 0 to 3 gigahertz kind of spectrum range. And all of these devices are loosely controlled by a network entity that we call a cognitive spectrum sensor and a server. And this could be either a single operator entity or a multi-operator entity. And the idea here is that all of the so-called small cells that you have distributed in a geographical region, they are also serving as a spectrum sensing entity. So they dynamically perform measurements under the control of the spectrum server. And these measurements are reported periodically to the broker, sort of the sensor. So the spectrum server is able to create, in a sense, a radio environment map, a logical, rather a location-based interference estimation map. And this map is then used to drive several operations. It could be used for doing better interference management. It could be used for better channel management. It can be even used for performing what we call better sensing. So if you and me are sitting pretty close to each other in a radio sense, we both don't need to do measurements at the same time. And you could optimize your sensing overhead dynamically in such a way. So the notion of sensing, scheduling, as well as managing of the interference spectrum resource, that functionality is built into the network resident entity that we call this as the spectrum server. So we have actually built this system. Currently, this system consists of two kinds of interfaces. So the top level is the white cell base station, and the bottom is the white cell client. They contain what we call as a stable interface, a license band interface, and they contain what we call as a white space interface. And our current white space interface is capable of operating in the entire UHF digital TV band in the US, which is from 470 to 700 megahertz. And we also interface with a FCC TV database server that is approved in US, one of the 9 companies that has been approved. We have live access to that TV database server. And our working system in Murray Hill actually talks to that server. And in the white space, we currently implement a variant of Wi-Fi as the baseband, essentially. But going forward, we are looking into implementing a TD-LTE-based baseband as well. And the main idea of having these dual interfaces is that whenever you need to do sensing operations, you move all your clients that are currently using a given white space channel into a stable license band interface. And when the sensing is finished and a new channel is allocated or the same channel is considered to be good, the end users have moved back into the white space channel. And the advantage of this is twofold. First of all, if you are using stable interface in the cellular band, it allows you to completely eliminate interference to your macrocellular layer majority of the time. You are interfering with your macrocell only for the durations of the sensing. So that helps you deal with the issue of how to minimize the impact on the macrocellular layer. And because you have this white space interface that is frequency agile, you are always guaranteed to try to find the best available channel in the given location. And on the client side, we also have an additional additional software layer that eliminates the disruptions that are caused by moving your sessions back and forth from the stable interface to the white space and back. And this is working, so if you're in Murray Hill, we can definitely show you a demonstration. And we can use the same prototype to do what we call near line of sight backhaul as well. So if you have, instead of this client device, think of this as a pole top mounted unit with 3G or 4G access on the client side. And the white space link essentially becomes a near line of sight backhaul. And we are currently working on outdoor demonstration of that as well. So if you have interest, if you are in Murray Hill, New Jersey, US area, let us know. We can potentially show this to you. And our radio actually that we are using is an experimental radio that goes from about 30 megahertz to 6 gigahertz with a few caveats. It's about the size of my palm. That's this kind of size that we are looking at right now. So I'll quickly run through the second case, which we call as this green cellular. And here the idea is how to make the network to be traffic adaptive and how to exploit your multi-band spectrum to reduce the energy in the network. So here's a simple illustration. We are showing essentially operation of a set of cells at 1 p.m. in the timeline and at 1 a.m. in the nighttime. And the center of those circles are essentially the base stations. And each base station has 4 sectors. So the small sectors have about an energy consumption cost of 10 units. And the large one, as shown on the right side, has an energy consumption cost of 15 units. So if I'm at 1 p.m., I require about 200 units of energy because all 16 sectors are active. But if I go to 1 a.m., I can have only 4 plus 4, 8 sectors, 4 small and 4 large sectors active. And that allows me to reduce my energy by a factor of 2. So the natural question is, can we do this in a real-time fashion throughout the day dynamically? And another idea that we have is, if I had to simulate those large sectors, can I activate my lower band of spectrum license in those sectors? So instead of activating a 2.1 gigahertz signal, can I activate a 700 megahertz signal? Because the 700 megahertz signal goes longer distance. So potentially my energy budget shrinks also proportionately. And we call that as a notion of spectrum dial. Essentially, I'm tuning down my spectrum dial to control my energy. And we intend to do that by exploiting the fact that majority of the operators have multi-band licenses. At least in the US, that's true. And I think as Caetano pointed out, even Telefonica is true. And can we extend that mechanism further to multiple operator scenario, where you have a notion of a multi-operator exchange, where one operator is willing to sacrifice his energy in exchange of a credit somewhere else within a spatial footprint as an energy trading mechanism. So we have actually built a real-time dynamic algorithm. And here's a quick screenshot that shows how the algorithm actually successfully does what it intends to do. So this is the initial configuration. The idea is that you have base station demands in a given region every 1 hour time window. And every 1 hour, you're going to run this algorithm to find out a configuration of base station powers and spectrum that optimizes the energy. So if I start with this initial configuration and run my algorithm, the final configuration is shown over here on the right side. And the idea is that it can successfully turn off a significant number of base stations and also assign the spectrum in process. Here's a quick chart that shows that our algorithm is actually, when compared to similar algorithm published in Mobicom just this year, does far better. And if I go to rural areas, the savings can be as much as a factor of 40%. In the urban areas, the savings are anywhere from 20 to 30%. So just to wrap up, we believe that dynamic access to spectrum and sort of integrated smart management of your spectrum assets are going to be key to making higher capacity as well as energy efficient cellular networks. And it can lead to new kind of market models as well as new kind of business models. And we as community need to definitely influence the regulatory agencies worldwide to make access to spectrum much more easier, especially when the technology is going to make it possible to do so. That's my sort of the message. So let me pause here.
Thank you very much for your presentation. There is space for a couple of questions. Well, I have one question. You talk about dynamic use of the spectrum and all the system from the network perspective, but my question is about the device perspective. Because I mean, the reality from an operator is that the complexity of the devices as time goes on in terms of capacity, in terms of processing power, in terms of even the number of frequency bands it needs to hold is really huge, accounting for the need of having something that is at a cost that is affordable for the people. So how do you think the technology and the scenarios today in terms of having the right devices for making this dynamic access to the spectrum happen? Because the complexity is probably an order of magnitude higher.
So you're absolutely right, I think. Am I on? Yeah. I think, so decidedly, the notion of getting your clients involved in spectrum measurements or getting them involved in dynamically accessing spectrum. That notion we are not entertaining in our work. Most of the work that we are doing is how to build the dynamic access capability within the network. And the clients are essentially signaled to follow the decisions that the network is making, right? So at the fundamental device design level, you do need the frequency tunability, you do need the spectrum agility. But from the additional work that needs to be done to access the spectrum on the client side, we do not want the client to be involved in those operations. We still want the client to be as much of a slave to the network as possible. So as to impact, not impact the energy consumption, not impact the complexity of the protocols that are involved. So you had a question, I think, so.
Question, and when you are switching off the cells or how do you handle the neighbors? So like the adjacency, everything is basically messed up.
Yeah,
so how do you do that?
That is not discussed over here, but how do you handle the session mobility when you turn on the cells? That definitely is a very critical question, and we are looking into what we need to do at the protocol level. What do we need to do in terms of moving the sessions to the cells that are going to remain active? That is still being work in progress. This is more algorithmic work, showing if those problems are tackled, how can I dynamically compute which cells to turn off without sacrificing the coverage constraints. So, but that's a very important question, how to.
Of GSM, so
yes, I agree.
It's quite complicated.
So, yeah, so this, I probably covered only one aspect of energy management. That is a very critical aspect too, and we are looking into that. So.
An additional question. When you talk about green energy and switching off the small cells, well, in the next 3 years, we'll be deploying small cells. With the time plan, the horizon, you may think that this could be available. In the sense that if we are deploying now the small cells, maybe we arrive on time or not?
I'm from research, so I think I prefer not to comment on the product availability, but these things are currently being worked on in the labs, and especially in the backhaul scenario, how to exploit wide space spectrum by using similar concepts. That's definitely much more immediate short-term availability, I would say, in terms of the bringing the concept of dual technology femtocell into more product space. I can probably take that offline with you later. So.
I was not referring to the femto, to the scanner, but to the switching off the small cells, the green energy concept. Is that, because there's a lot of uncertainty, as David said, the neighborhood, the management of mobility. Is this concept completely work that maybe in 3, 4, 5 years this will be ready, or is more long time period?
Harder to give a timeline, I would say, but this work is being done, as you know, as a part of the Green Touch Consortium, where the idea is to do pre-competitive technology creation, right? And so the technology creation is going to happen in the next 2 to 3 years, and probably from that point on, it will come to market. So it's longer than